Hello everybody. Today we're going to talk about section 7.3, which is trigonometric substitutions. Okay, so our objectives for today is to evaluate integrals involving quadratic square root of a quadratic expression, okay, using an appropriate substitution, which is a very special substitution that we had never used it up to now. And second thing is to use the idea of the completion of the square. Okay, so we're going to solve such integrals. So for example, you will have 1 over x squared times square root of 1 minus x squared, and the integral of x cubed over square root of 4x squared minus 1, and the integral of 9 minus x squared over x squared, and the integral of x over square root of x squared minus 4x plus 5 with respect to x. So we're going to solve such integrals which involve square root of quadratic expression like those. Okay, actually we saw some integrals before that involve a square root of a quadratic equation. For example, we know how to solve such integral, which is the integration of -3 to 3 for the square root of 9 minus x squared dx. Actually here we know that this function represents a circle, or actually it's half of a circle, it's a semicircle. So if you write y to be square root of 9 minus x squared, so you can square both sides and then get the x and y in the same side, so you will get x squared plus y squared equal 9. Okay, so if you try to graph it, you will have a circle centered at 0 and its radius is 3. Okay, but since this square root is positive, so we will deal only with the upper semicircle. And then we know that the definite integral is the same as the area under the curve, so we can interpret this integration as the area under the curve. So it is going to be the area under the area of a semicircle, which is half times pi r squared, which is 3 squared. So we know how to solve some integrals which involve square root of a quadratic equations, for quadratic equations. Okay, but let's see another example. Okay, also you know how to solve this integral. I think this was the one which was in the first method. So the integral of x times the square root of 16 minus x to the power 4 dx from 0 to 2. So also you know how to solve this one, because if you use this substitution, so u equal x squared, so u equal 2x dx. So and x is changing from 0 to 2, so u will change from, when you substitute with x equals 0, it will be 0, and when you substitute with x equal 2, u will be 4. So this integral I can be written as follows. It will be the integral from 0 to 4, and then you have x dx, which is x dx is half du, so we can write half before the integral sign, and then we have du. Okay, and then you'll have the square root of 16, okay, minus x to the power 4, which is now is u squared. So again, this is the equation of a circle, or of a semicircle. And then so if I graph it, it will be something like that. Okay, it's centered at 0, okay, and this is the x as u-axis, okay. So and then from 0 to 4, so I'm talking about this part of the circle. So the area under the curve, it will be the same as this definite integral, which is the quarter of the area of the circle. So it will be half times 1 over 4 by r square. R here is 4, so it will be 4 square. Okay, so we know also how to solve this a little bit complicated examples which involving a square root. Also, let's see another example where we can use the idea of the completion of the square. So another example. So the integration from 0 to 4 for this square root, which is 4x minus x squared dx. So actually, you can use the idea of the completion of a square here. So we can rewrite this as, if we call it I, so we can rewrite as from 0 to 4, and that's square root of negative times x squared minus 4x with respect to x. So by using the completion of the square, you will have negative, and then you will have this square bracket, you will have x minus 2 all squared, and then you have to subtract 4 again, so you'll have something like this. So I is going to be, so I equals the integration from 0 to 4 for the square root of 4 minus x minus 2 square dx. And actually, again, this is a circle. If you call, if you let u, for example, to be x minus 2, okay, so this integral will be the integration. So x is changing from 0 to 4, so u will change from 0 to 2, okay, and then you will have the square root of 4 minus u square, and u is the same as dx because it's linear and the coefficient of x is 1. So you will have this integral. So it will be the area of the quarter of a circle. So if you graph it, you will have this semicircle, and then you're talking from 0 to 2. So you're talking about this area. So again, this area is going to be 1 over 4 times pi r squared, and r here is 2. Okay, so somehow we know how to solve such integrals which involve the square root of a quadratic expression. But we did that using the geometrical interpretation. So we handle our integrand such that somehow it represents a circle or the area of a function that such that we can calculate the area under the curve. Okay, but what about the next examples? How can we deal with them? What if I ask you to calculate this integral from 0 to 1 for 9 minus x squared dx? Okay, maybe you say, yes, again, this is the equation of a semicircle. So if you graph it, you will have something like that. This is a semicircle with radius 3, but here we're talking about the area from 0 to 1. So here is 1. So the area from 0 to 1 is this portion of the circle. So actually, we don't know how to calculate this portion of the circle, because we know how to calculate the area of a semicircle or of a circle or of, you can say, of a regular part of a circle. So we need another method. So let's see another example. What about this one? It looks like the same as the first one, but here's x plus 9 plus x squared dx. Even it was from 0 to 3. Yeah, but here actually this is not a circle. This is not a circle. So you cannot use this geometric interpretation anymore. Okay? So also, what about this one? 1 over x squared times 1 minus x squared. Again, it's not a circle, and it's more complicated. Okay? And many other examples. Now I think we can begin our lecture. So we need a special substitution to solve some of these integrals. So let's begin with this example, which is 1 over x squared times the square root of 1 minus x squared with respect to x. Okay, So let's call this is I. So actually all the time you write u as a function in x, okay? But maybe this doesn't work now, so we will define a new substitution which is called inverse substitution. Here we define our new variable as a function in x, but we're going to do the other way around. Now you know the inverse function, so we will define x to be a function in a new variable, which is theta, and we will put some restrictions such that on theta, such that this function to be one-to-one, I mean to be invertible. Okay, so here we're going to use this substitution. Actually, we know that sine squared theta plus cosine squared theta equals 1. So I will use this identity to define my substitution. Okay, I will choose x to be a function in theta, such that x equal sine theta, and everything. So x will be sine theta, and everything we will do it for sine theta. I think you can do it for cosine, so you can use sine or cosine. Okay, and then I will put restriction here on theta, such that this function to be invertible. Okay, so if you grab this function, so the sine, we know the sine function is not invertible. Okay, but if we restrict ourselves to this region, which is from negative pi over 2 to pi over 2, our function will be one-to-one function, and it will be invertible. Okay, so we will put this restriction. So theta will be from negative pi over 2 to pi over 2. Okay, and we will see why we need this restriction actually. So I have two reasons for that. The first one, that you can talk about theta as a function in x, so you can write theta as sine inverse x. And the second one we will see in a minute. So now we need to get rid of this square root. We're looking for this substitution to get rid of this square root. So let's calculate the square root of 1 minus x squared. So it is going to be 1 minus sine squared theta. Yeah, and now we can use this relation here. It will be the square root of cosine squared theta, which equals the absolute value of cosine theta. The square root of x squared does not equal x, because we know that the square root is a positive function, so the square root equals the absolute value of x. Okay, so the cosine, the graph of the cosine is something like that. Okay, from negative pi over 2 to pi over 2, we can see that the cosine is a positive function in this interval. Okay, so actually we can remove this absolute value. Okay, and we can go and solve directly. Okay, so anyway, all the time when you have a square root of 1 minus something squared, or a squared minus x squared, you're going to use this substitution with this restriction. Okay, I will make a summary for that, don't worry. Okay, so we saw why we have to use this substitution. Okay, we will use this substitution, which is x equal sine theta so when you have a square root like that, a squared minus x squared, so you have to use this substitution, which is x equal a sine theta, or a cosine theta, and theta is between negative pi over 2 to pi over 2. Okay, so we're going to use this substitution now. Okay, so here we have this square root, which is 1 minus x squared. So x equal sine theta, and dx equal cosine theta d theta, and theta is between negative pi over 2 and pi over 2. So if you use this substitution, you will have I equals the integration of 1 over x squared will be sine square theta, and then the square root directly will be, as we see, the square root will be, okay, again, the square root of 1 minus sine square theta times dx, which is cosine theta d theta. Okay, so I will be the integration of sine square theta, and here is 1, and this will be cosine square, and then the square root will be absolute value of cosine, and since our theta is between negative pi over 2 and pi over 2, so our cosine is positive, so we can write cosine theta, and then here you have cosine theta d theta, and then you can cancel this cosine together, and then you will have 1 over sine squared, which is cosec square theta. Okay, and then you know how to integrate cosec squared. What is the function when we differentiate it? We get cosec squared. Yes, exactly, which is negative tan theta plus constant. But our integral was in terms of x, and now it's in terms of theta. So we have to rewrite everything again. Okay, so we will do that in 2 ways. Okay, so we know that x equals sine theta. Okay, so you can, the first method is to write this triangle. So theta, so sine theta is opposite over hypotenuse. So this is x and this is 1, and this is 1 minus by Pythagoras, 1 minus x squared. Okay, so now if I want to calculate cotan theta, what's cotan theta? Cotan theta equals it is the reciprocal of the tan, so it will be the adjacent over the opposite. So it will be square root of 1 minus x squared over x. Okay. Okay. So now we can say that this is the first method actually. Okay. And the second one is to use the identities of the trig functions. How? So we know that the cotan theta equals cosine over sine. Cosine theta over sine theta. And we know that the sine theta is x, and the cosine theta is square root of 1 minus sine square. So it will be square root of 1 minus sine square theta. So the cotan theta will be square root of 1 minus x squared over x. Okay, so you can use it here. So instead of, you replace cotan theta by its value in terms of x. So it will be negative square root of 1 minus x squared over x plus c. And in this way we did it. Okay, so let's give a brief summary for this example. You have an integral, and you want to and you find that in the integral there is a square root of a quadratic expression. Okay, since this is with the form square root of a square minus x squared, so you have to use this substitution, which is x equal a sine theta, and a here is 1, so x equal sine theta, and then you will get dx, which is cosine theta, and then you have to substitute here, and you calculate everything, and you get the value of the integral, but you will find it in terms of theta. Okay, so to rewrite it, you have to rewrite everything in terms of x again. So you have 2 ways, since we have this substitution. So if you consider x is if you consider theta is positive angle, okay, so so you can have this triangle, and then you can find the value of the cotan theta, or you can use the identities of the trig functions. For example, cotan theta equals cosine over sine, and the cosine equals square root of 1 minus sine squared. So in terms of sine, you can replace sine by x. So now you will have square root of 1 minus x squared over x, and then you can use the value of the cotan to rewrite everything in terms of x. Okay. Okay. So now let's see another example. Example 2. Okay. We want to solve this integration. I equals the integral of x to the power 5 over the square root of 4 plus x squared dx. Okay, so now we have a square root of a quadratic expression. So we know this this identity, that 1 plus tan squared equals secant squared. Okay, so if you choose x to be 2 tan theta, so if I choose x to be 2 tan theta, why 2? Because this is 4, so I have to take the square root of this number and write it here, and then since this is plus, so I will use tan squared. Why? Because if you try to calculate 4 plus x, the square root of 4 plus x squared, it will be the square root of 4 plus x squared. Here is 4 tan squared theta, so you can take 4 as a common factor and it will be 2 when you get it out of the square root, and then you will have the square root of 1 plus tan squared, which is secant squared. So when you take the square root, it will be secant theta in the absolute value. So if we choose theta to be restricted by from between pi over 2 and negative pi over 2, so actually the secant is 1 over cosine, and the cosine is positive function inside this interval, so this will be the same as 2 sec theta. Okay, so if we use this substitution with this restriction, we will have we will get rid of this square root by 2 sec theta. Okay, okay, so let's try to use this substitution to solve this integral. So now you have x equals 2 tan theta, so dx will be 2 sec squared theta d theta. Okay, so let's use this substitution. So our integral will be the integration of x squared, so we will have 2 to the power 5 times tan to the power 5 over the square root of this, which of 4 plus x squared, which will be 2 sec theta, times dx, which is 2 sec squared theta d theta. Okay, so we can cancel these 2 and this secant, so we'll have 2 to the power 5 before the integral, and then you have integral of tan to the power 5 times sec theta d theta. Okay, so actually, as we saw in the last section, when you have the power of the tangent is odd, you can use this trick. Okay, so you can separate one tan here, so we'll have sec tan. Okay, and here you will have tan to the power 4 theta. Okay, so and then you have to rewrite tan to the power 4 as in terms of sec, so it will be sec squared minus 1 all square. Okay, so directly with this substitution, as we saw in the last section, so u equals sec theta d theta, so du will be sec tan, so I will be 2 to the power 5, and then the integral of instead of sec squared we will write u squared minus 1 all squared, and then instead of sec theta tan theta you will have du, you will have d theta or du, and then easily you can solve this one, because this is the same as u to the power 4 minus 2u squared plus 1. So I equal 2 to the power 5, then the integration of u to the power 5, u to the power 4 is u to the power 5 over 5 minus 2 u cube over 3 plus u, all this plus c. Okay, and now we can replace u by its value, which is sec theta, sorry. So I equal 2 to the power 5, and then you have sec theta to the power 5 over 5 minus 2 over 3 sec cube plus sec theta, all of these plus constant. So we have to replace the sec theta by its value in terms of x, but actually we had this substitution. So again, we have two methods to do that. The first method is to draw our triangle. If this is theta, so tan theta is x over 2. Tan is the opposite over the adjacent. Okay, so this is going to be 4 plus x squared. So if I want to write sec theta, so sec theta equals, which is the reciprocal of the cosine. So the cosine is 2 over the square root, so it will be the square root of 4 plus x squared over 2. So this is the first method. The second one is to use the trig identities to do that. We know that tan theta equals x over 2. So sec squared theta equals 1 plus tan squared. So it will be 1 plus x over 2 squared, okay, which can be written as 4 plus x squared over 4. So sec theta will be the square root of 4 plus x squared over 2, okay. So you can substitute here and you can write I in terms of x. You replace sec theta by its value, okay. So in this way we done this example. So again, let's give a brief summary for this one. Here you had a square root of 4 plus x squared, and we said that if you have a square plus x squared, so you have to use the substitution, which is x equal square root of a squared times tan theta. And with this substitution, we get rid of this square root, and then we solve the new integral using what we know from section 7.1. Okay. Okay. Now let's see another example, which looks like the last one. So we want to solve this integral, which is x over the square root of 4 plus x squared dx. Okay, maybe, okay, you can say, okay, we have a square root of a quadratic expression, so we have to use this trig substitution. Okay, but actually this is much easier than that. How? That this integral can be written as x times 4 plus x squared all to the power negative half dx. And with this substitution, with the usual substitution that u equal x squared, okay, or u equal and with this substitution, which is 4 plus x squared, okay, so du will be 2x dx, and our integral becomes you have x dx will replaced by half du, and then you will have this, which is 4 plus x squared, which is u to the power negative half, and which is easy to integrate. So this is du, okay. So you will have half times u to the power half over half plus c. So you can cancel this half with this one, and this, and then you will replace u by its value. So you will have 4 plus x squared all to the power half plus c. Okay, so sometimes you don't need actually this substitution for this easy example. So don't make it more complicated. So if you know a better substitution than the new one, the trig substitution, so use it. Okay, sometimes it's just 1 or 2 lines. Okay. Another example, example 4. So we want to find this integral, the integral of x cubed over square root of 4x squared minus 1 with respect to x from 1 to 2. Okay, so again, you know that 1 plus tan square theta equals secant square. Okay, so secant square minus 1 is the same as tan square, which is the situation here that you have something which is squared, which is 2x all to the power 2. So, okay, minus 1. So actually, it will be a good idea if we use this substitution. So 2x will be sec theta. Okay. So, and we will put this restriction on theta. So we will write theta from 0 to pi over 2. And we will see why we have to have theta in this way. Okay. So here x equals half sec theta. So dx equals half sec theta tan theta d theta, and x was changing from 1 to 2. So x is changing from 1 to 2. So theta will change from with easy calculations you can prove that theta is changing from pi over 3 to cosine inverse of 1 over 4. Okay, so let's see why when x equal 1 theta is going to be pi over 3. We will substitute here, let x equal to 1, so it will equal half sec theta. So in this way sec theta equals 2, which means that cosine theta equals half, so theta equals pi over 3. Okay, and the same for the other one. Let's let x equal 2, so 2 equal half sec theta, which means that 4 equals sec theta, so cosine theta equals 1 over 4, so theta equals cosine arc cosine of 1 over 4. Okay, so this is why theta will change from pi over 3 to this value. Okay, so now let's use this substitution to solve our integral. So I will be the integral from pi over 3 to cosine inverse of 1 over 4. And then you have x cubed here. X cubed will be 1 over 8 times sec cube over the square root of this one. So the square root will be, this is 2x all square, so it will be secant square minus 1 times dx here, which is half times sec theta tan theta d theta. Okay, so I will be, so here before we continue, so this will be the square root of tan, this will be the square root of tan square, so which is the absolute value of tan theta. But since we restrict ourselves for theta from 0 to pi over 2, so the tan, we know that the graph of the tan is something like that. Okay, and then it's periodic from pi over 2 to, from negative pi over 2 to pi over 2. So if we restrict ourselves from 0 to pi over 2, so tan is positive. So tan is positive, so the absolute value can be removed. So I will be 1 over 16, and then the integral from pi over 3 to cosine inverse of 1 over 4. Here you'll have sec cubed times sec, so it's sec to the power 4 theta, and here this tan will go with this tan, so you will have sec to the power 4 theta d theta. So as we saw in the last section, if the power of the secant is even, so it's recommended to separate sec square factor, and then you will have sec square. And then you have to write everything here as a function in tan theta. So you will have 1 plus tan square theta. So now our integral will be I equal 1 over 16, and then the integral of 1 plus tan square theta from pi over 3 to cosine inverse of 1 over 4 times sec square theta d theta. Okay, so we can easily solve this integral. So if we distribute this sec square here, you will have the integral of sec square theta plus tan theta all squared times sec square theta d theta, and here you have 1 over 16 from pi over 3 to cosine inverse of 1 over 4. Okay, and easily you can integrate sec square. So the integration of sec square is tan, so you'll have 1 over 16, and here you'll have tan theta. You know that the differentiation of the tan is secant square, so this integration will be tan cube over 3, because simply if you differentiate this one you will get this, and okay, and all this, and theta will change from pi over 3 to cosine inverse of 1 over 4. Okay, and here, since this is definite integral, you don't need to rewrite everything in terms of x, because from the beginning this integral is a number. Okay, and in this way we done with this example. Now let's give a brief summary of what we have done up to now. Okay, so consider that you have this expression, okay, which is square root of a square minus a square, and so you have to use this substitution, which is x equal a sine theta, where theta is restricted between negative pi over 2 and pi over 2. Okay, and the idea here is to use this identity, which is 1 minus sine square theta equals sine square theta. So in this way your square root a square minus x square will be a times the absolute value of cosine theta, and since this theta between negative pi over 2 and pi over 2, so it will be just cosine theta. Okay, so this is the first case. The second case, if your integrand involve this square root of this quadratic expression, which is a square plus x square, so here you have to use this substitution, which is x equal a tan theta, and theta is restricted between pi over 2 and negative pi over 2, and the idea comes from this identity, which is 1 plus tan square theta equals secant square theta. Okay, so in this way the square root of a square plus x squared will be a times the absolute value of sec theta. So, and since we restrict ourselves here, so the absolute value can be removed, so it will be a sec theta. And finally, if you have this square root, which is x squared minus a squared, so you have to use this substitution, which is x equal a sec theta, and theta is restricted between 0 and pi over 2, or theta between pi and 3 pi over 2. And the idea comes from this identity, which is secant square minus 1 equals tan square. Okay, so the square root of x square minus a square will be a times the absolute value of tan theta, but since our theta is between 0 to pi over 2, or between pi to 3 pi over 2, so there is no meaning for this absolute value, because tan is positive in these intervals, so the square root will be replaced by a tan theta. Okay, So now let's see another example to know how to use the idea of the completion of the square. So our last example, which is example 5. So our integral is the integration of x over square root of x squared minus 4x plus 5. So here you have under the root you have a full quadratic expression, so you have to use the idea of the complete square. So here this is can be written as x minus 2 all squared minus 4 plus 5. We know how to make a complete square. So this integral will be the integration of x over square root of x minus 2 squared plus 1. Okay. And now you can easily think about x minus 2 as x. And since this is something x squared or something squared plus s squared, so we have to use this substitution, which is x minus 2 will be tan theta, and theta is restricted between negative pi over 2 and pi over 2. Okay, so the x equal sec squared theta d theta. So our integral I will be the integration of x here is 2 plus tan theta over the square root of x minus 2 all squared plus 1. So it will be tan squared plus 1, which is secant squared, and under the root will be sec theta without the absolute value, because theta is between negative pi over 2 and pi over 2, times dx, which is sec squared theta d theta. So after simplification you can find that this you want just to evaluate the integration of 2 sec theta d theta, or 2 times the integration of sec theta d theta plus the integration of sec theta tan theta d theta. So we know how to integrate this one from section 7.1 or even before that. So we know that the integration of the secant is ln sec theta plus tan theta, okay, plus the integration of sec tan is sec theta plus constant. And it remains for us to rewrite everything in terms of x. And again, you can do the same two methods. Our triangle here. Okay, so if you consider this is theta, if you consider this is theta, so and tan theta is x minus 2, so it will be x minus 2 over 1. So here this will be the square root of 1 plus x minus 2 all squared. From this triangle we can see that tan theta again is x minus 2, and sec theta, which is the reciprocal of the cosine. The cosine here is 1 over this square root. So it will be the square root of, so sec theta is the square root of 1 plus x minus 2 all square, which is the same as using this rule, this identity, that secant square equals square root of 1 plus tan square. Okay, since we know that this is the value of the tan, which is x minus 2, so it's the same. Anyway, you can use any of these two methods. So our integral I will be 2 times ln sec theta, which is this is square root 1 plus x minus 2 square, okay, plus tan theta, which is x minus 2, and then plus sec theta, which is the square root of 1 plus x minus 2 square, plus c. And in this way we know how to use the idea of the completion of the square in this situation. So again, if you have such an integral and you have a square root of a full quadratic expression. So first you have to make a complete square, and then you have to use these trig substitutions if it needed. So this was our lecture for today for section 7.3. So see you in section 7.4.